Great. Yeah, so welcome everyone. Thank you all for coming to today's event. Let me quickly mention a few words about Quantum Serbia. So Quantum Serbia is a community of enthusiasts, professionals, students, mostly from Serbia of Serbian origin. The goal is to promote quantum technologies and quantum computing in Serbia and the region, and to organize events such as this one, to collaborate, to learn more, and to connect with people. Of course, we are open to also other interested people of other nationalities. As you can see, this talk will be in English. We welcome everyone to join our social groups. Like we have a group on meetup.com with more than 600 members. We also have LinkedIn and other social media. This talk will later be uploaded to YouTube, and you can also check it out there. I can share it with someone that couldn't make it. And yeah, so let's then proceed to the introduction. So today we have a great privilege to hear a talk from one of Serbian most esteemed professors of physics, Professor Vladan Vuletić. He's a professor at the Department of Physics at the Massachusetts Institute of Technology. He was born in Peć, Serbia, and he studied physics in Germany. He earned his physics diploma with highest honors and his PhD in physics from Ludwig Maximilians University at Munich in Germany. And he also worked with Nobel laureates, Professor Hensch and Professor Stephen Chu. He published over 150 refereed articles and received numerous awards, including a Sloan Research Fellowship, Fellowship of the American Physics Society, and Marko Jarić Prize from Serbian Faculty of Physics in Belgrade, and also the Tesla Spirit Award. Today, Professor Vuletić will be presenting on a topic called the quantum age, from Bell pairs to quantum computers. He will discuss the development of entangled Bell pairs, quantum simulation with atomic arrays, and prospects for near and medium-term neutral atom quantum computers. And without further ado, Professor, please.
Thank you very much, Radojica, for the kind introduction. Just a moment. My pointer and then okay. So it's my great pleasure to be with you today. I would like to tell you about what I think is the coming quantum age, and I would like to put our own work and research that I will tell you about in the context of the 2022 Nobel Prize, which honored the measurement of so-called Bell pairs and entanglement and experimental observation of some of these very surprising features of quantum mechanics that I would also like to tell you about. So I would like to explain to you a little bit about the foundations of entanglement, or what is also called quantum correlations. Especially Einstein had a problem with that. He didn't believe it. It was largely thought to be a metaphysical question until John Bell came along and turned it into an experimental question that could be answered. And last year's Nobel Prize was given for the experimental realization of these tests that, proved Einstein wrong and proved quantum mechanics as we understand it today right. And this is these so-called Bell pairs. And these were experiments done with photons, where it's easy to generate pairs of entangled correlated quantum systems. But then I would like to tell you about atomic systems that we use, where we achieve what we call now quantum simulation, and where we hope to achieve full-blown quantum computation over the next few years. So what is this Einstein-Podolsky-Rosen paradox that Einstein had a problem with? Well, it turns out that in quantum mechanics, you can make pairs of particles, and you can make them in such a way that you don't know the position of particle one. This is indicated by these circles of different colors. So each time you do a measurement of, say, the position of particle one, you find the particle in a different position. And similarly, if you make a measurement of the position of particle two, you find it in a different position, but what you find is perfect correlations. So whenever you measure, the blue position for particle one, you measure the blue position for particle two. And when you measure the yellow position for particle one, and you measure the yellow position for particle two, etc. So somehow the position of each particle is known, but what we call the correlations between the particles can be perfect. And it turns out that you can make these quantum mechanical states such that these correlations are not only true for position, but similarly, if you measure, for instance, the velocity or what we call momentum of a particle, you would also have a situation where the momentum or the velocity of the particle, of each particle individually, would be uncertain, but where they would be perfectly correlated. So whenever you measure a certain amount of velocity of particle one, you would measure the same velocity to the other side for particle two. And Einstein had a big problem with that, because he says, this is impossible. It seems the momentum position cannot have reality at the same time if, I cannot measure them simultaneously. What also comes out of quantum mechanics is that when you measure the position, you disturb the momentum and vice versa. So Einstein didn't really believe in it. He said, the Lord God doesn't throw dice. Physics should be deterministic. And so he came up with this so-called paradox, where he said how absurd this is, and that this, would never be observed like this. He believed that there was a local reality that would tell you, for instance, exactly what position particle one would have and what momentum it would have without having to refer to particle two. That was his view. And if you look, I looked up the citations of Einstein, and to my surprise, this Einstein-Podolsky-Rosen paradox is by far his most cited paper. So if you look at his top papers, this is his paper on special relativity to elektrodynamik bewegter Körper. So that's kind of fourth on this, top list of publications. And this third one is the so-called Brownian motion paper. The second one is the one he actually got the Nobel Prize for. This is the so-called photoelectric effect, where he figured out, how individual photons exist and create individual electrons. And then this Einstein-Podolsky-Rosen paper, which was ignored for many decades, has now become a hit because people can actually measure these systems. So what is this about? And even classically, there's somehow an interesting question where information reside. Imagine for the moment that we have a box which contains one white and one black ball, like so, and somehow we shoot out these balls towards two observers that we call A and B, or conventionally Alice and Bob. So we don't know which ball will go to which side. So we don't know whether Alice will receive a white ball or a black ball and vice versa. But what we do know is as soon as Alice receives the white ball, she immediately knows that Bob has the black ball, and vice versa. So you can ask yourself, where is the information really residing? And is it residing in the individual balls, and is it somehow non-local? Is it residing somehow not at all in space? How do we think about this problem so that we have a randomness, but we have correlations? Now, it turns out that, if we had just these classical correlations, it wouldn't be super interesting. We would be used to that, but it turns out that quantum correlations are much stronger than classical correlations. So what corresponds to two colors classically, a black and a white ball, actually quantum mechanically corresponds to what we call a two-state system. So two possibilities that we will call 0 and 1, in analogy to classical computing, where a bit can have, a 0 or a 1 value. However, classically, a bit can be either in the state 0 or 1, whereas quantum mechanically, it can be simultaneously in the states 0 and 1 with some additional degrees of freedom, what we call a superposition. So it can be simultaneously in both states 0 and 1. And furthermore, there can be also what we call a phase. So there are different superpositions of 0 and 1 that are possible. So it turns out that quantum mechanically, this two possibility system, which classically is just 0 or 1, has quantum mechanically one way to describe it is that it lives on a sphere. We call this the Bloch sphere, and this sphere has different directions. For instance, the state 0 would correspond to this vector, this arrow pointing up. The state 1 would correspond to the vector pointing down. A superposition of 0 and 1 would be pointing somewhere in the equatorial plane, depending on the phase. So for instance, this direction would be 0 plus 1, but we could also have 0 minus 1, or 0 plus the complex number I times 1. So quantum mechanics also has complex numbers. So this basically means that the quantum mechanical system is much richer than the classical system, and that we can measure correlations, for instance, not only in the basis 0 and 1, do we measure a black or a white ball, but we can also measure them in superpositions. What superposition of black and white ball do we measure? This is what it looks like quantum mechanically. And then the way people realized this EPR paradox was actually not with position of momentum in particles. That was at the time too hard. But we used instead polarization states of photons. So photons they have an oscillating electric field, and we can think of oscillation in one direction as say 0, and oscillation in another direction as 1. But then the polarization can also oscillate, for instance, along the diagonal, which would be 0 plus 1, or it can be so-called circular polarization, which would be 0 minus 1. And so with polarizations of photons, therefore, we can easily realize the measurements if we can somehow create these two photons, two particles that are entangled, that are quantum correlated, such that we don't know the state or the polarization of each individual photon, but we know the correlations between them. On this kind of sphere, it would mean that we can't predict in which direction we will measure this arrow pointing, this vector pointing, but we know, for instance, depending on the correlations, that whenever we measure a certain direction on one sphere, which is completely random, we will measure exactly the same correlation on the other sphere, even if the two photons are far apart, in principle, even light years apart. And so then the big mystery for Einstein was, how is it possible that the information from the left travels to the right, if that's even the right way to think about it. And so, Einstein had called this paradox, but then John Bell came up with this idea that one can actually test Einstein's view, namely that there's local reality compared to the quantum view, which somehow says that there are quantum correlations even for far apart particles that cannot communicate with one another. And so Bell came up with an inequality of certain correlation measurements, basically measurements along different directions of different polarizations of photons. And he showed that this inequality that I've written symbolically here would be obeyed by local hidden variable theories of the kind that Einstein preferred. So this particular type of correlation would be less than 2 for Einstein's view, but it could be violated and would be violated by quantum mechanics. So this was a way that suddenly allowed one to test this Einstein's paradox and possibly confirm or exclude local hidden variable. Particularly, he came up with so-called Bell states. This is a state 0, 1, minus 1, 0. What this state really means is that if I measure down or a photon down or one polarization in one direction, then I measure an arrow up for the other direction and vice versa. So the state of each photon is completely undetermined, but there are perfect correlations, in this case, anti-correlations, vectors pointing in opposite direction for the two photons. And it turns out that for this particular state, it's uncorrelated at any basis that you can measure. So basically, whenever you measure, Alice chooses her basis to measure, and if Bob measures in the same basis, he will always find the arrow pointing in the opposite direction. So in this sense, because you can make these different measurements and Alice has the freedom to choose her measurements, these quantum correlations are much stronger than classical correlations like the black and white ball. And so this was a way to test this. And the first one to test this was John Clauser, one of the Nobel Prize recipients last year, who did experiments in the 1970s. He managed to make entangled photons by having atoms emit pairs of photons, and then he analyzed the polarizations of the photons, which represent these states, and he measured in particular the correlations between these photons, and he was the first to show that the measurements agreed perfectly with quantum mechanics and actually disagreed with this Einstein view that there was local reality to the photons. So somehow these correlations were non-local. How did John Clauser make these photons? It sounds like it might be very hard to make these strongly quantum correlated in entangled state. Let me give you an idea. So these are atomic energy levels, and he prepared atoms in an excited state. And this excited state was chosen in such a way that it could decay back to the ground state down here, but it could decay via two different paths. So for the experts, what I've written down is the so-called angular momentum of the atoms, but it's not so important. What is important simply is that the atom can either decay by emitting first a photon of one polarization, we call this circular polarization, say a right-handed electric field oscillating, and then a left-handed electric field oscillating. And this combination of, the photons having two different circular polarizations is has to do with so-called conservation of angular momentum in the whole system. So basically, you can first emit one type of photon in a red color and then another polarization of photon in the blue color. But it's also possible to go the other way around. You can emit the other circular polarization of the photon as a red color and then the sigma plus photon as a blue color. So these two pathways are possible, and there's nothing in the world that distinguishes them, so they happen at the same time. So when an atom emits a photon, it simultaneously emits those two paths. And it turns out that this is enough to make entangled photons, because you can see they are correlated in the sense that whenever the red photon has positive circular polarization, then the blue photon has negative circular polarization, and vice versa. And so this creates an entangled state, and this is what John Clauser used to make these measurements. The actual level scheme is shown here. It's not very important. This is the basic idea. Alain Aspect from Paris then made these experiments better and more interesting. So what he did is he let the photons travel for a while, and then he made the measurement decisions, what Alice would measure on the left. So you can think of this apparatus as Alice and this apparatus as Bob. He made these decisions so fast that the fastest signal that we know of, namely even light, could not be able to transfer the information from the right to the left side and vice versa. So he closed the so-called locality loopholes. He made measurements simultaneously so fast that there was no way of communication via the speed of light between the two parts of the apparatus. And this showed somehow that these correlations had a non-local character. There was no way information could travel. And he became famous for these experiments. And then Anton Zeilinger from the University of Vienna, he even made more random situations. So in Alain Aspect's experiment, either the experimenter or the computer chose these directions in which to measure the polarization of the photons. And Anton Zeilinger used photons from very distant galaxies from different parts of the universe that had never even communicated in the past to set these random measurements. And in all of these cases, quantum mechanics was confirmed. Anton Zeilinger also invented a new way to make beta pairs of entangled photons at larger rate. Basically, he used a single blue photon and converted it into two red photons, and we could arrange the situation such that they were still entangled with one another. And with this, Anton Zeilinger could also make what is called now quantum teleportation. Basically, he could teleport the state, in this case, the polarization state of one photon to another photon that had never interacted in the past with the first photon. So by making entangled pairs on the left and entangled pairs on the right, and then performing certain measurements, correlation measurements on the middle two photons, he could transport or teleport the state from photon 1 to photon 4, even though these photons had never interacted with one another in the past. And so this brought also this concept of so-called quantum teleportation to the forefront. So he made entanglement between photons that had not interacted. So maybe this is a good moment to pause and see if there are questions about this.
Yeah, so I don't see any questions currently in the chat. Maybe we'll give a few seconds. I don't know if someone wants to ask something.
If not,
can I ask a question? So I don't want to be controversial, but I'm confused. I'm not a physicist, so I don't know. So I read some comments about Penrose and Thorne, who are also Nobel Prize winners, and they might think that there is Einstein or EPR guys were at the end right. because maybe of quantum gravity. So what do you think about?
I mean,
there are more and more voices about that.
There are certain other possibilities, and this belt pair measurement only excludes so-called local hidden variable theories, where the information is stored locally, but not necessarily what you could call global hidden variable theories. So I would say that there are other ways around it. These experiments exclude a particular type of hidden variable theories, but of course, you know, in physics and in science, we learn, and maybe there are some ideas that we don't know about yet. I would say at the moment, you know, quantum mechanics has passed many tests with flying colors, and we have no direct indication that it is wrong, but I wouldn't exclude it for the future.
Thank you.
So maybe we can continue now. So these are all experiments with photons, and they are very nice. They can travel very fast. They're easy to prepare, but it's hard to make larger systems than a few photons, because, you know, photons travel very fast. You can't really store them. They can easily be lost. So what I would like to tell you about is now systems where we entangle atoms. Atoms are, you know, there's more work to be done, because you have to, you know, you have to basically trap and cool the atoms to be able to hold on to them and so on. But if you can do that, and I show you that we can, then you can keep entangled states for longer times, and you can also make much larger entangled systems. So as I said, photons are almost ideal carriers of quantum states, but they are difficult to keep over more than a few hundred microseconds. They don't have strong interactions, so it's difficult to entangle them on demand unless they were entangled at creation. And it's, as I said, it's hard to make large states. Atoms are more difficult to control initially, but we have learned how to laser cool them to temperatures very close to absolute zero, where the atoms can be trapped, for instance, in light trapped in focused laser beams. We have also learned how to make strong interactions between them on demand. I will show you about it. And quantum states can be stored for a long time. By long time, we mean seconds, tens of seconds, maybe hundreds of seconds, enough to perform quantum manipulation of them. So let me tell you about this field of atoms that we now call quantum simulation and quantum computation. So first, we need to generalize this idea of logic. So, and this is called quantum gates. So classical bits have state 0 or 1, and computers work with these classical bits by performing Boolean classical logic gates. For instance, there's the AND gate where the outcome is only 1 if, say, both bits are in the state 1, or the OR gate where the outcome is 1 if one or both of the atoms are in state 1, etc. And so it turns out that this concept of classical logic can be generalized to quantum gates. And this shows you one of the famous quantum gates, a so-called controlled NOT gate. And in this system, you have, like in the classical system, 2 bits. We call them now quantum bits because they can be in a superposition state. And the idea is that the state of the first atom here, or first qubit, first quantum bit, controls the state of the second qubit. And the rules for this controlled NOT gate, for instance, are that if the first atom is in 0, then the state of the second atom remains unchanged. So you can see that as these 2 first lines. Basically, if the first atom is in 0, then 0 maps onto 0 for the second atom, and 1 maps onto 1. But if the state of the second atom is in the 1 state, then of the first atom is in the 1 state, then 0 maps onto 1 and 1 maps onto 0. And so this is generalization of this Boolean classical logic. And we also assume that in quantum mechanics, this works also for superpositions of states. So for instance, if you prepare the first atom to be simultaneously in 0 and 1, say for instance 0 minus 1, and the second atom in 0, you apply this so-called C0 gate, and then you can see that you can deterministically, using these rules up here, generate a so-called Bell state. In this case, a Bell state where the atoms are perfectly correlated. So you don't know whether the first atom will be in 0 or 1, but you know whenever you measure the first atom in 0, then the second atom will also be in 0. So if you have the so-called quantum logic, you can create Bell states of more complicated systems. And here, these ideas about so-called quantum simulation go back to Richard Feynman, one of the famous physicists of the last century, who already in 1983 proposed the following. Now we can, in principle, and I will read this quote to you, make a computing device in which the numbers are represented by a row of atoms with each atom in either of the two states. These are the states R0 and 1. That's our input. Then the Hamiltonian starts. Hamiltonian for physicists is this, basically this interaction that can make, for instance, controlled NOT gates and other manipulations. The ones move around, the zeros move around. Finally, a particular bunch of atoms represents the answer. Nothing could be made smaller, nothing could be made more elegant. And at the time when Feynman proposed it, I think it looked crazy to almost everybody. He had this idea, but nobody thought one could control atoms. But I would like to show you that now we have actually realized something which, kind of mirrors or maps this prophetic quote. So let me tell you how to control individual atoms. This goes back to an experiment by Philippe Granger and his students and postdocs in Paris, now over 20 years ago, where he basically had a vacuum chamber. The reason why we need vacuum is because if we did these experiments in air, then any atom that we want to control would be bombarded, colliding with molecules in the air. So we need a very good vacuum so that there are very few particles so that we can hold on to the atom for a long time. And then what he did is he took a laser beam and made a tiny trap for an atom, focused to about 1 micrometer. And it turns out that, if you choose the right frequency of light, this can act as a trap for atoms. And then he also used other laser beams to cool the atoms. This had been invented by Stephen Chu in the 1990s. So one can laser cool an atom to microkelvin temperature with about absolute zero, so to minus 273 degrees Celsius plus a millionth of a degree. So these are situations where the atom speed is very, very small. Atoms at room temperature move, say, at a few hundred meters per second, but these atoms, they move slower than ants. So they are very, very slow, and they can be held onto with laser beams. And then as he cooled the atoms and observed it, observed it simultaneously on a camera, he found that basically the signal on the camera consisted of just 2 different levels. A level that is just background, no atoms in there. There's a little bit of scatter light on the camera, various sources, and then a higher level that was, constant for a while, that corresponds to 1 atom. So basically what you see here is an empty trap, a trap loaded for 1 atom, empty again, loaded, etc. And these atoms would stay in the trap for 4 seconds at a time. So he showed that with these tiny focused laser beams, you could trap 1 atom, but as you can see, the atom was in the trap for only 50% of the time. And so that made it very hard to scale things, because if 1 atom is only there 50% of the time, and say you want to trap 10 atoms, then the probability of trapping these 10 atoms simultaneously would be exponentially small. So for a while, this was not much pursued further. And then we did in 2016, in collaboration with Misha Lukin's group and Markus Greiner's group at Harvard, these are 2 of my physicist colleagues at Harvard, we did an experiment where we said, well, Philippe Granger could observe the atoms, so what we can do is we can just look, and whenever an atom is in the trap, we can just do something with the atom, we can apply feedback. So the idea to make many atoms rather than just 1 was this observation and real-time feedback. So the way we did this experiment, instead of 1 laser beam, we focused many laser beams, in this case 100 laser beams, into a vacuum cell where we laser cool the atoms. We can make these 100 laser beams out of 1 by a so-called acousto-optic deflector for the expert. This is a device that basically takes a radio frequency input, and each tone, each frequency of the radio frequency input creates a different laser beam. And so basically by controlling your radio frequency signal, you can control these traps. You can turn them on and off. You can move them around by changing the frequency, etc. So we made this array of atoms and of beams. And then we started loading it with atoms. And so what you see here is actually a movie slowed down somewhat. And each of these white points here is actually an atom. So a microscope is looking at these atoms. These atoms emit light as they are being continuously laser cooled. And then basically what you see here is a string of 100 traps, and they are randomly loaded. So some of them are full. Whenever you see a white spot, that's full. But then there are also some empty traps in between. So a computer looks at this image, analyzes it, and then controls the trap to make a quasi-deterministic string of atoms. So basically what happens is the computer looks at the picture, determines which traps are empty, turns off these traps, and moves the other traps in such a way so that we can make most of the time deterministically strings of maybe 30, 50 atoms or so. This movie has been slowed down, but you can see we can now, for the first time, we could at the time deterministically make strings of 30 up to 50 atoms at a time in one dimension. So this is just an example. Again, this is not a cartoon. These are actual real images of atoms where we make a random string of atoms and then we move the traps in such a way to make almost perfect strings of quite a large size. So for me, it's quite remarkable that, maybe a little bit more than 100 years ago, atoms were still, kind of a theoretical concept. And now we can see them in the lab, in real time individually. So we then expanded this to 2 dimensions. Now we have a 2D array of traps. This is maybe 300 traps or so, randomly loaded. And then basically by doing some similar sorting algorithm, we can make these almost perfect 2-dimensional arrays of individual atoms with, in this case, about 150 or so, up to 200. We can sort them in 2 dimensions. We can make these arrays. These atoms, just to give you an idea, this whole picture here is about the width of a human hair. So it's about 100 to 200 microns or so. So this is a very, very small volume, and the distance between the atoms is about 3 micrometers in this picture. So this whole thing kind of is at the cross of 2 human hairs, roughly speaking. So it's a small volume, but we can control them. So we can now make these individual atoms that we can regard as quantum bits. We can control the states of these atoms. And then you can ask, well, can we make gates between them? Before I show you that, what we did in 2D can also be done in 3D. This is a colleague of us. From this picture, you can guess where he comes from. This is an Eiffel Tower. So he made an Eiffel Tower in 3 dimensions out of trapped atoms, a cone, something like a bucket ball, so-called fullerene, or a torus, etc. So one can even control these light traps in 3 dimensions. Again, as you see on the scale of a human hair, width of about 100 micrometers. And so these are laser-cooled atoms at ultra-low temperatures, 1 millionth of a degree above absolute zero. And then the next question is, now we can make these atoms. Can we actually implement these quantum gates? Can we make them interact? Can we entangle them in interesting ways? The atoms, as I showed you, are a few micrometers apart. And there, again, 20 years ago, my colleagues, Misha Lukin, who I already mentioned, Peter Zoller, Ignacio Cirac, Dieter Jaksch, and so on, came up with an idea to make atoms interact over long distances, basically by exciting atoms to very high-lying states. These are so-called Rydberg states, going back to the work of Johannes Rydberg, who was a Swedish scientist in the 19th century, who studied highly excited atoms. So for those of you who know about the hydrogen atom can have different energy levels. There's a ground state and then an excited state, and they have many, many excited states. So these Rydberg atoms correspond to the, like 50 to 100 principal quantum number excited states. These are very highly excited states, and they are special in the sense that the electron is very far away from the nucleus. So for these highly excited state, the electron is 10,000 times further away from the nucleus than in the ground state. Basically the atom is 10,000 times bigger than a normal atom. And that means that atoms can also interact over large distances. Serge Haroche won the Nobel Prize in 2012 for work with Rydberg atoms, but not using them the way we do, but for other types of interactions, but also entanglement. So these are very interesting atoms. So for us, basically, it means that the interaction strength over optical resolvable distances corresponds to, we like to express strength in frequency units because that tells us the speed of gates. And so this corresponds to megahertz. So this means, roughly speaking, that we can make entangled states on a time scale of 1 microsecond or maybe 100 nanoseconds or so. So basically, the stronger the interaction, the faster we can make these states. So we can basically turn on and off the interaction between atoms that are trapped in these arrays over optical resolvable distances. And so the way it works is as following. We have, this two-level system, the ground state of the atom and then the so-called Rydberg state of the atom that we view as these quantum bits, and we drive them with a laser beam, and so we can make superpositions of these states. And if these atoms are further away than a characteristic distance, what we call blockade radius, then basically you can excite each of these atoms to its Rydberg state separately. However, when they are closer together than a blockade radius, then what happens is if you excite the first atom to the so-called Rydberg state, then the Rydberg-Rydberg interaction is so strong that the second atom cannot be excited to the Rydberg state anymore. There's a very strong interaction between them, which allows you to make these quantum gates, to make this Boolean logic or quantum logic between atoms, and allows ultimately for entanglement, quantum simulation, and computation. So that's the basic principle. And so the idea is that if you try to excite the system, you can excite the left atom or you can excite the right atom, but never both. And since you don't know which of these situations is actually true, you create a superposition or entangled or a quantum correlated state between these two atoms. This is really just for the experts. If there are any physicists in the audience, the so-called Hamiltonian, the interaction energy. If you're not a physicist, just ignore this. But if you're interested, basically this interaction has three terms. One term that is controlled by the laser intensity, and is basically Rabi flopping, a flopping of the atom from the ground state to the Rydberg state back to the ground state, described by the first term. There's a detuning term in here, which controls the energy of the state, and then there's this interaction term that prevents two atoms from being excited. But the physics is basically this Rydberg blockade and these quantum gates. We have applied these systems to two different types of system. We have done analog simulation of, for instance, an optimization problem. Let me tell you briefly about this. So this is a problem that is very hard to compute. It's a so-called graph problem. So I'm giving you a graph, which means I'm giving you, vertices indicated by these circles, and I'm giving you connections between them. For instance, these connections could be some, say, if this is Facebook, this connection could be whether you're friends with another person, or if this is, your cell phone, then this connection could be, the distance between your cell phone and the nearby tower that you can reach or not reach. So you're given this graph, and one of these problems is to say you have this graph, is you should try to color as many vertices as you can on this graph, but you're never allowed to color any vertices that are connected by a line. So basically, this is in this friend picture, if you are in this excited state, then none of your friends is allowed to be in the excited state. So it turns out that this is a computationally, classically very, very hard problem to solve, because these graphs can have general situations. So in this case, for instance, on the right, I showed the solution for this particular graph. So we ask ourselves, can a quantum simulator do better or differently than a classical computer? So here's, for instance, a network that we were trying to encode. We place them on a square line, and then all these lines between them indicate connections between vertices, which prevent which we are not allowed to populate. And then we ran this quantum simulator, and this is the solution that it came up with. This is the best solution, except for one error on this side. So you can see it's highly non-trivial to come up with the best solution of which of these vertices to color, so that they are not connected to any other vertex, and to color the largest number of vertices. And so when we compared the performance of the quantum simulator to the classical simulator, we found that there was a quadratic speedup. So if measured in some natural units, basically the quantum simulator took only the square root of the time that the classical simulator would take as we make this problem larger and larger, and therefore the hardness parameter larger and larger. So this is nice, but for the future, we hope not only for a quadratic speedup, but there's theoretical works that indicates that it should be possible, at least for certain problems, to achieve an exponential speedup, so much, much larger speedup than this classical speedup, but it was a nice step forward. Some of this work was done by a company that we have founded here in the Boston area, a startup company. And the startup company uses the systems that we first demonstrated at the university to offer services. So there's now 300 or 250 atom machine available for access. And if you're interested, you can basically use this machine, this quantum simulator, via Amazon Web Services. It has been available since last October. And researchers are using this, for instance, to model various quantum systems and try out new algorithms for computation and for simulation. So this is so far an analog machine. Now I would like to tell you finally in the last few minutes about so-called digital quantum machines, where we really do quantum gates. So here we looked at how well can we do quantum gates. This is basically the flopping of a single qubit between the two states. So this system shows you that we can nearly perfectly, with an error of about 2 × 10⁻⁴, change the state of a single qubit and take it from the ground state to a controlled superposition of 2 states to an excited state and back down. So these single qubit operations are very, very good already at the level of 10⁻⁴ error or so. We also can do 2 qubit systems. So these quantum gates, the C0 gate that I told you about. So this is a C0 gate. And again, the quality of these oscillations indicates something about the quality of the gate that we can make. At the time of this publication, our errors were about 2.5%. We have now pushed them down to 0.5% or so. We also looked at, can we move these states? And I would like to tell you about so-called quantum error correction, which is essentially for the performance of classical computers. Error correction is essential for the performance of quasi-computers, and I would like to tell you how that could work. So what is classical error correction? So, there can be errors even in a classical computer. Logical bits can flip. The way we solve this is we encode the same information, the same what we call logical bit, in several copies. This is an example where we encoded a several bit in 9 copies, 9 physical bits. And then if some of these flip, say maybe an X-ray, goes through your hard disk, or there's some other, source of error, then maybe 2 of these bits might flip, indicated by the red ones. And then what you do as a classical computer is you look at them and you say, okay, 7 of them are still in the 0 state and 2 of them are in the 1 state. Well, the 2 in the 1 state must be wrong, and I'm just going to reset them. And so that way you constantly correct for errors in the system. You make the classical computer very, very robust. You could say, can I do this in the quantum realm? But in the quantum realm, the problem is, in order to keep these superposition states, these entangled states, you're never allowed to look at the qubits. So the quantum state must remain unobserved. So you're not allowed to look, is the atom in state 0 or 1? And that might make you think that maybe quantum error correction is simply impossible and doomed. But then people came up with a very clever idea. They said there is a way to measure, and people propose theoretical several ways. There's a way to determine whether several copies of a logical qubit, several physical copies, are in the same state or not, without ever revealing the actual state of the bit. And this is a pictorial representation of a so-called surface error code. So the white circles in here are actually multiple physical copies of the same logical qubit, shown here in the grid. And then these black circles here are additional quantum bits that we use for error detection. So for instance, if in this example, this particular physical qubit had flipped state, we are not allowed to look at it. But what we can do is we can perform certain manipulations, certain logical gates between these error syndrome or ancilla qubits and these various qubits. And then what we would find is that these ancilla qubits would all light up in a way that would tell us that this particular qubit has made an error, and then we can just flip this qubit without ever looking at it. So this has been theoretically proposed and shown to work, but it hasn't been demonstrated in practice yet. So for that, I would like to show you that we can entangle pairs. So basically what you need to do is you need to be able to entangle these ancilla qubits with this memory qubit and then read them out somehow in a separate region. So first experiment we did was to entangle pairs, then transport the entanglements, so 100 micrometers or so, and then bring the atoms back and check, are they still correlated? And we could see no difference between the entanglement, the quality of these quantum correlations between the stationary qubits when we didn't transport them, and the ones we transported, as long as the average speed, as long as the transport speed didn't exceed about a meter per second or so. So we showed that we can transport entanglement perfectly in these systems. And that allowed us to demonstrate the first ingredient for quantum error correction. I will show you that. So in this particular movie, you will see stationary atoms, these dots that don't move. These are the physical copies of a logical qubit, if you want. And then you will see atoms that are moving around. These are moved around by moving laser beams around. These are the so-called ancilla qubits. And each time I draw here a red circle, this means we perform a quantum gate, a controlled NOT gate between these. And so basically each ancilla qubit, as you will see, will become entangled with 4 different physical copies of the memory qubit, and then will be transported to a different region to be read out. So this is what it looks like in a movie. So we entangle 1, entangle 2, entanglement 3, entanglement 4, 1 more for some remaining qubits. Then we bring these ancilla qubits, the syndrome qubits, to this region where we look for errors. And what we could show is that the ancilla qubits, to something like 80% fidelity, showed us, or correctly indicated, the errors that had happened in these so-called physical qubits. So this is not error correction yet, because what you need to do now is to integrate this whole thing in a feedback loop. You need to measure these atoms in real time fast, and then feed back to these memory qubits, to these physical qubits, to reset the ones that have had an error, in order to show that you can keep a quantum state on your quantum computer forever. And we are intensely working on it. And because we can move these atoms, we can not only realize planar geometries, but we can also realize, for instance, geometries in 3 dimensions, effectively in 3 dimensions on a torus, that, for instance, have some better properties for quantum error correction. So this brings us to what we're working on now. The idea is that we will have these atoms that can be moved around, moving around these laser beams in a computation region like so. We will have another region where we can read out the ancilla qubits, and then we are trying to do this quantum error correction for the first time to demonstrate that we can keep a quantum state for much longer. I should point out that there are other companies working on other concepts. Google in particular has a very, very large effort and is also attempting, or has very interesting work on quantum error correction. They use different types of qubits, so-called superconducting qubits, whereas we use neutral atoms. And both of these systems have their own advantages and disadvantages, but it's currently a race between different platforms to realize larger and larger systems. And where we are now with the atoms is we have scaled things up now to a few hundred physical qubits, and we hope to be at thousands or maybe 10,000 qubits within a year or so. And that brings me to my outlook. So entanglement has transformed for a surprising, or as Einstein viewed it, disturbing concept into a useful tool. Large-scale entanglement, both collective spin states and individual controlled spin, is now possible. We have made entangled states of tens up to hundreds of atoms. I think we will scale very quickly to 1,000 to 10,000 qubits within the next 2 years. Quantum simulators are also useful for science. I didn't have time. Already useful for science. I haven't time to tell you about it. But quantum error correction seems, we hope to be there within a year or so. And then basically one is in a situation to explore quantum algorithms. And this is an open field of research. Quantum algorithms are kind of harder to figure out, to think about, to invent than classical algorithms. There are a few proposed. The most famous one is a so-called Shor's algorithm, which is the problem of prime factoring, of taking a very large number and finding the prime number factors that compose that number. So many groups theoretically in the world are working on quantum algorithms, and we will be excited if we can realize quantum error corrected computers to try out these algorithms on these machines and see how they work. And with this, I'm at the end, and I thank you for your attention.
Thank you very much, Professor, for the wonderful talk. Let's see if there are any questions. Yeah, please write them in the chat or interrupt us to ask. So there is one question asking, I'll maybe rephrase it. What are maybe some advantages and disadvantages of these systems compared to superconducting qubits?
That's a very good question. Superconducting qubits are around longer. So this is a new system. Only in 2016, for instance, we learned how to control many atoms. The advantages of superconducting qubits are that they can use fabrication techniques that are established in making classical computers. So basically they are fabricated in solid state. The disadvantages are that when you make these quantum bits artificially, then any variations in the production lead to variations between the qubits, whereas atoms are identical by the laws of physics. So if you take, we work with rubidium atoms, if you take two rubidium atoms, they are perfectly identical with each other. So our systems are kind of easier to scale. The superconducting qubits use existing fabrication technology. We use optical access, they use microwaves. So it will be an interesting question. Interestingly, at the moment, we are it's a neck-to-neck race, even though these are very different physical systems.
Thank you. There is also a question. I mean, you mentioned the application about in graph theory problems. And do you imagine, you showed some quadratic speedup, but do you imagine that there is something more like to it for some general hard graph problems? Like, can they maybe be applied to some other graph problems, etc.?
That's a very good question. It's an active area of research. What we suspect, and we are looking at that, is that there are certain types of problems, even within this graph problem, other graph problems, that are, so there are certainly certain type of problems that are, relatively easy for classical computers and maybe harder for quantum computers, but there we suspect there's also a whole class of problem or class of, configurations rather than problems that are easier on a quantum computer than a classical computer. So in that case, you would use a hybrid processor, which would try to solve the problem both classically and quantum mechanically. And we think that there are instances, and we see a little bit of evidence of that, where the quantum computer actually can solve problems reasonably fast that a classical computer has a hard time on. So it may very well be, and that's an open question, that if you look at this whole space of possible configurations, that there's a certain overlap, so certain problems are easy for both classical and quantum simulators, but then there might be non-overlapping regions, and so that might already be a reason to include quantum simulators to basically use it as a co-processor in some way with a classical computer. But it's very much an open question right now, and different groups are looking at this both theoretically and experimentally.
Yeah, I agree. I mean, so it would be wonderful if that was the case. There is a special class of problems that are quantumly easy. Yeah, there is another question. Are there any plans for QERA to go public like IonQ? And can you compare this approach to trapped ions?
That's a very good question. So ions were the first platform where quantum gates were demonstrated already in the late 1990s or mid-late 1990s. So these are similar to the neutral atom approach in the sense that lasers are used, but these are charged particles. So instead of holding them in laser traps, they are held in traps of electrodes that produce electric fields. QERA is not currently planning to go public. We will see, but QERA is at the moment focused at solving the technical problems first. So we don't think we need a very, very large startup for that. Ion traps are also neck to neck in some sense. Ion traps have advantages in the sense that you don't have to move ions around. They can communicate with each other over longer distances because they are charged. They do have currently a problem of scaling things up. So when you load more than 50 or so ions into an ion trap, it seems that there are unwanted interactions and heatings that are hard to solve, but they are working very actively on that. So yes, I should have said that, the third platform also neck to neck is the ion trap quantum computing platform. And we'll just see who wins the race in the end, or maybe, several platforms will simultaneously be successful in implementing real error-correct quantum computers.
Thank you. There is another question. Do you think that quantum RAM is feasible, and are we getting any closer to being able to implement it?
So this would be basically to store quantum states. There are many interesting ideas out there. It depends what you mean by implementation and what particular scheme. In some sense, we can already write quantum states into a memory and read them out. But to do that on a large scale might be possible. There are many interesting ideas out there. I'm not sure I can definitely answer this question, how close we are to realizing some of them.
Okay, thank you. I have a question as well, so it's maybe a bit technical. So for example, for these graph problems, I mean, throughout your talk, you mentioned a lot about entanglement and how it's some special feature that cannot be replicated classically. But do you think it's actually the entanglement that might allow us to do well in these optimization problems, or maybe like these final states that are reached in these optimization procedures might not have high levels of entanglement at all?
That's a very good question. It's a debated question. It's clear that entanglement plays some role. So you can show that when there's no entanglement, there's no speedup, and where there's too little entanglement, at least of a certain type, there's very little speedup. On the other hand, it is also true that what we think of as the most entangled states, the states that are most sensitive, are not necessarily the ones that are used in a quantum computer. So it's not like you need to create maximum entanglement or all possible entangled states in a quantum computer to use it for computation. So it's an open research area. It looks at the moment like the ability to compute and the ability to entangle are somewhat overlapping, and you need entanglement for speedup, but you don't need every type of entanglement, and you don't also need the largest entanglement for speedup. That's what it looks like right now. But it's an open question of our understanding. How are entanglement and measures of entanglement and ability to compute related?
Yeah, great, thank you. Maybe another one. I know it's hard to predict the future. I mean, we mostly don't know what application will be the most successful, but which application of quantum computing is closest to your heart, and you can imagine it, or maybe you would like it to happen in the next decade? Or
in this field, just even like in classical computing, but even harder, it's notoriously hard to prove that certain algorithms are better than other algorithms. So I think just like when people built for classical computers, I think they didn't have a clear idea of what would work really well and what wouldn't, because if you need a mathematical proof, that's just very hard. So what I certainly hope for is to have these machines that allow people to invent different algorithms and try them out, and then basically learn how these algorithms scale, right? Something like we did for this graph problem. We look at the scaling properties and see, will it eventually outperform classical computers? So what I would really love to have these machines available to as many people as possible who are thinking about quantum algorithms, and then try them and learn what are, possible ones and not. But it's very hard to invent useful quantum algorithms, and the only one that we really know about, mathematically proven that works, is the famous Shor algorithms. And that one, of course, would have impact in the sense that it would break quantum cryptography. It would break basically the way we encrypt information, for instance, on the internet now, and we would have to look for new ways. But my idea is hopefully people get to use these machines, get to figure out, as many as possible algorithms that there are, and we learn how to make useful algorithms with these systems.
Thank you. There's another question in the chat. So what do you think that students and researchers from Serbia should focus on when trying to get into the field of quantum computing? Do you have any recommendations, and what are your advices?
Well, of course, experimentally, these are very big efforts and relatively expensive machines, although, you know, it depends. These are still tabletop experiments. Certainly the threshold on the theoretical side is much lower. And then there are many research groups, there are many startup companies too that are looking at, you know, the quantum software side of things. And so to learn about quantum mechanics, certainly, and then maybe get involved into some kind of research and develop ideas is an entryway into this field, I would say.
Thank you. I guess we already out of time. It's been an hour. So thank you, Professor. If you have something to add, please feel free. Otherwise, I guess we'll wrap up.
I would just like to thank everybody for coming, and it was great to interact with you, and thank you so much for this invitation. I really enjoyed it.
Thank you very much.